Hi, this is ET250 Lecture 15, and today we're going to start our discussion on AC. And before we start talking about AC, we need to review our trig, so our trigonometry. In that review, we're going to talk about radians, cosines, sines. I have this other variable called tau that I'll introduce. You might not have heard of it, not torque, but kind of a replacement for pi. We'll look at sinusoids with time, and we'll look at this new form VP cosine of omega t plus theta. And I know that seems like a lot now, but if you've never seen it, but it shouldn't be too bad. And this will become a friend of yours, especially when we talk about AC power. We'll look at the relationships between omega, the frequency, period. We'll also look at this phase guy and try to get an intuition of what it means. Basically, a bigger phase means it leads, a smaller phase means it lags. We'll look at the time that the peak of this cosine occurs, all right? And then we'll look at some examples, and I'll introduce this concept called the root mean square, or RMS. And there's actually a nice relationship between the peak or amplitude and the root mean square. It's just a factor of root 2. We'll do an example and actually plot this example in Excel, right? Just so that you can see how these variables will change a sinusoidal plot, and you could actually go in and make changes too. Okay, so let's begin. So let's start off with a very straightforward trigonometric function, y equals cosine of theta. And you have to just, this is just something you got to memorize, guys. When theta is 0, cosine of 0 is 1. Okay, and then from there, you can make your plot. And what's the outer limits here, the range? We go 1 to -1 here. And you can see this is a quarter cycle, half a cycle, 3/4 cycle, 1 cycle. And I think you can remember from your trig that this is, 90, 180, 270, 360 degrees, or pi over 2, pi, 3 pi over 2, 2 pi radians, right? So no problems there, just a good review of what cosine is. Okay, what about sine? Well, sine of theta, it looks like this. It's just shifted over by 90 degrees or a quarter cycle. And you have to remember that sine of 0 is 0 and that it's on the increasing, right? It's tempting to say, well, sine of 0 equals 0 over here. Yeah, that's true, but this is the decreasing side. So you just have to memorize that sine of 0 equals 0 and it's increasing. It's the same thing, quarter cycle, half a cycle, 3/4 cycle, 1 cycle, same angular displacement here. Okay, so gotta lock, this has to be, especially this one, because we're gonna be dealing with cosines a lot. You really gotta lock cosine into your brain, okay? All right, now you see radians, and maybe like me, when you first were introduced to radians, it was like, what is a radian? And still, even after lecture, you're like, well, I don't quite understand what a radian is still. Let's remind ourselves, what is a radian? Okay, so I think radians are good. It's actually a good thing because when you're calculating power, when you're calculating energy in a rotational sense, radians are natural. It's very good. In fact, 90, 360, the only reason why we're comfortable with it is because we've been introduced to it at a very young age, right? Really, degrees is, I think it's an old Mayan kind of introduction or something like that. But, and I think it has to do with like every day out of the, calendar, the year, sorry. But it's not very useful when you go beyond one revolution, right, or one cycle, because then you're like, what, 720, and then it's like, oh, I got to add 360. That's painful to do, right? I mean, I have to be honest, radians are the same way, right? But the nice thing is they don't have to have any factors when you calculate power, right? And so that's nice. So let's look at why. So let's look at a unit circle here. We have a unit circle here, and we have some radius, right? And a radian is a unit of the angular displacement theta found by dividing the corresponding arc length by the radius, okay? So this is the definition. All right, fine. Yeah, you've probably seen this in your trig lectures. Notice something, S and R are both units of meters. So radian is technically unitless, and here's a picture of it. So if I had a unit circle, it doesn't matter how big the unit circle is. This could be a 1 meter unit circle, a huge unit circle, or it could be like 0.1 meters. It doesn't matter. You can imagine that the theta wouldn't change, right? These would all scale proportionally, right? So this arc length corresponding to this theta divided by this radius that's how we define a radian, Okay, so it's a meter divided by a meter. Okay, fine. Let's go in and let's try to get a little bit of intuition on a radian. So if I asked you, well, how much is one radian then? Like, is it like this? Is it like this? Is it like that? What is 1 radian? Well, it's when this is 1, when S over R is 1. Well, that means they have to be equal, right? So what we can do is we go, well, what is S when this is equal to R? Wouldn't it be something like this? Yeah, this is your S. When this S equals R, this is 1 radian. So that's what 1 radian looks like. That's what it feels like a piece of pizza, right? That's 1 radian. Okay, so 1 radian, if you're close, is 57 or about 60 degrees, right? 60 degrees, 57 degrees, that's about 1 radian. So when you hear 1 radian, I want you to have that intuition that it's about 60 degrees, okay? It's about 1/6 of a circle, okay? I hope that sticks. I really want that to stick. 1 radian is about 1/6 of a circle, about 57, 60 degrees, okay? So now look at this. If I were to just count how many radians are in a circle, yeah, 1, 2, 3, 4, 5, 6, yeah, like I said, but there's actually a little bit extra. There's a little bit extra, and that extra is 0.28. And so that should be that familiar number. 6.28 radians is 1 revolution or cycle around the circle. Okay, so hopefully some of this is hitting home. Maybe for some of you, like, of course, this is obvious. I remember all this. But maybe some of you, it's rusty. It's like, oh, yeah, I forgot. Okay, this is a good review. Okay, so 6.28 radians is 360 degrees. 2 pi radians, what revolution is 6.28? Because pi, we know, is 3.14. 3.14 times 2 is 6.28. Good. We know pi is half a revolution, 180 degrees, right? So these are all common things. We have it memorized, but I don't know if we have it intuited, like I get it, I understand, I can visualize it. Does that make sense? So hopefully this helps you visualize what a radian is, how many radians are in a circle. So if I said there's 12 radians, you're like, oh, that's 2 circles, about a little bit less, right? Okay, then the next question might be, what is pi? Well, okay, we know pi is 1/2 a revolution, 180 degrees, but why and where did it come from, right? This is a weird, arbitrary, like, I don't know, constant, right? Well, this is where it came from. They just defined it as this. Well, if we take the circumference and divide it by the diameter, then that's pi. And that's true, right? You can see that there's 1, 2, 3. So if this is a diameter, there's about 3 diameters in a circumference, right? Yeah, that makes sense. Okay, a little over 3 diameters in 1 circumference, and hence you get C equals pi d, right? And you guys remember this formula, C equals 2 pi r. Well, this is where it comes from. This is the definition, right? This is actually just a reworking this equation, like when you go from radius to circumference. This is just the definition of the pi kind of reworked, right? And so we can easily see that pi is well, not easily, actually, it took them a while to figure this out, that it was 3.14159, a rational number. You know, people have competitions memorizing, you know, these digits. It's just like, you know, sick. I don't know. Some people, anyway. So you have this number here. This is the ratio of the circumference to the diameter. Fine. Okay. So let's look at sinusoids with time. Okay, well, actually, you know, even before that, I think I'm a little bit, before I do that, I want to actually bring this up. This is I don't know if you can sense in my tone. This is a slight little rant. So I found this YouTube video. You can Google it. I'll try to find the link, put in the description. Tau Manifesto. And it convinced me. Radians are good. Pi is bad, right? And I'm like, yeah, pi is bad. Pi is confusing. I don't know if I really liked pi ever in the first place. People are like, oh, we have Pi Day and all that good stuff. And yeah, sure, pi is delicious. But maybe it's, what is it, June 28th is a better day, right? Okay, what if we had defined a new variable, a new constant, tau? And tau is, instead of the circumference of the diameter, is the circumference of the radius. okay? And so we define tau as 6.28 directly, okay? So none of this pi business, right? Still, radians are there, right? We didn't make radians go away, right? I like radians for power and all that stuff, but let's do an example. So let's go back to that y equals cosine theta business, right? And so we kind of already saw this. So if I have y equals cosine of theta, theta is in radians, and I use my pi, you guys are okay. 2 pi is 1 cycle, pi and a half, 3 pi over 2, 3 pi is here, 4 pi is there. To me, that's confusing. I'm sorry. 2 cycles, 4 pi. I mean, yeah, I know it's just a factor of 2, and you're like, mathematicians might go, come on, Evan, it's just a factor of 2. Don't be dumb. But I'm like, oh, okay, yeah, but what about 3 pi? And I have to go, okay, 1.5. Yeah, okay, get it. But can't we do something easier? Why make our life hard when we don't have to, right? Life is already hard. All right, so let's look at this. What if we defined everything in tau, right? Still radians. I didn't make radians go away. I like radians. Radians are good, yay. But look at this. 1 tau is 1 cycle. 2 tau is 2 cycles. 1.5 tau is 1.5 cycles. Half a tau is half a cycle. 3/4 tau is 3/4 of a cycle. 1/4 tau, well, it's 1/4 of a cycle. That's intuitive to me. That's confusing. The sad thing is, I'm probably still going to keep the pi notation in the rest of the lectures. I'm sorry, but and it's because the textbooks and the rest of the world still knows pi. No one has adopted really tau, right? If I say tau, they're going to think torque or something like that. Like, what are you doing? But I just want to bring this up to highlight, could we make things better, right? Could we make things better? So, anyways, just a thought. Tau Manifesto. Google it, check it out. I'll try to remember to put a link in the description. Okay, let's keep going. Okay, so let's look at sinusoids with time. And so like here, we had the x variable as theta, okay? Well, what if we want to have this as time, because that's going to be related to AC current and voltage, right? Okay, so this is going to be our new formula. Now notice this argument, that's how we say it on the street. The stuff in the parentheses, that's called the argument, okay? So this argument is actually still angle. That doesn't change. But notice within the argument, we have omega t plus theta, all right? Okay, what happens here? Well, in the original one, it's the angle that varies. Here, we're making the time vary. Now, if the time varies, this argument varies, which is still an angle, but we're using time as the independent variable now, okay? And so now let's see what happens. So I should be a little bit careful. This is theta v, right? That's theta v. So what do we have here? We have a phase, we have a frequency, we have an amplitude, right? And I think this one, let's start with this one. This is actually pretty easy here. Remember, cosine goes from -1 to 1, right? -1 to 1. If I add a constant out here, then it's going to go from negative v peak to positive v peak. Okay, that's easy. Okay, what is this omega and theta going to do? Well, first of all, let's just get rid of this. Let's just say theta equals 0, right? And even if omega is a non-zero number, let's say t equals 0. So if theta equals 0 and t equals 0, well, this whole thing equals 0, and you actually just have cosine of 0. So in this case, when theta equals 0, cosine of 0, you get 1, right? And 1 times v peak. So you actually get this point right here, right? Now, as time varies, this argument varies, and this whole thing is going to increase, and you're going to get this, okay? You're still going to get a sinusoid, but notice how the x variable is time now and not theta, okay? All right, what's the distance between here and here? We call that a period, 1 period time, right? Okay, so the time between cycle to cycle. Okay, great. And so let's define a few of these things. V peak, okay, great. Amplitude, t is period, technically in seconds. This is unit of seconds because we're on the x-axis. It is the seconds per cycle. That makes sense. That's the definition of it, all right? What is theta v called? We call this the phase, and it can be in radians or degrees. Now, if you're going to add these two, you got to be careful. So let's look at the units. So omega is the angular frequency. That's going to be how much this squishes. So omega is actually units of radians per second. So this would have, look at this, radians per second times time, which is seconds. This variable changes, right? This is a constant, this is a constant. And so yes, this could be in degrees, but if we were to actually make a computation, this would have to be converted to radians, or this would have to be converted to degrees to make sure these match in units to be able to punch this in. Okay, and then your calculator would have to be set appropriately to radians or degrees to calculate this. Okay, and then time here is just the x variable, and that can change. Do not confuse this with period. Okay, I know this is a lot, but let's keep breaking it down and trying to add in more intuition. Okay. Okay, we have this concept of frequency, right? We're like, okay, I know that we have, what is it, 60 hertz. 60 hertz as our fundamental frequency for our electricity, right? And frequency is defined as cycles per second, no problem. Hertz, right? Hertz cycles per second, okay. And actually the frequency is the inverse of this period. Okay, nice. Wait, so how does this frequency and this, well, we got this relationship between the frequency and period. I don't see the period or frequency show up in here at all, right? None at all, right? No T, no capital T and no F. But yet, do they contain the information of F and T? They sure do. And it's all encapsulated in that omega. Omega is 2 pi F, okay? This is how I convert cycles per second to radians per second, right? Now, I put the 2 pi. What is 2 pi? You look at that and you're like, oh, what is 2 pi again? I mean, we just talked about it. Remember, it's 6.28 because there's 6.28 radians in one cycle, right? Because I'm trying to convert cycles per second to radians per second. Or we could think of it as 1 tau. So technically, yeah, we could say this is a tau F, where this is equal to 6.28. Actually, I can even put it here on my notes, 6.28 F, right? Okay, sneak that in there, right? Okay, so given omega, F, or T, you can find the others. It's a 3-for-1. That's kind of nice, right? 3-for-1. If I give you F, I can find T. If I give you F, I can find omega. If I give you omega, I can find F. And if I have F, I can find T. Can you guys see that this is a 3-for-1? So yes, the information for the frequency or the period is embedded in this omega using these two equations. Okay. This is just a unit conversion, and this is just understanding that frequency and the period are inversely proportional to each other, right? So a frequency of 1,000 hertz is equal to a period of 0.001 seconds. That makes sense. Okay. And a frequency of 1 hertz is equal to an angular velocity of 6.28 radians per second, or tau radians per second, or 2 pi radians per second. Okay, good. So the bigger omega is, the more squishy this becomes, right? Because the period is going to get tighter and tighter and tighter. If omega gets bigger, F gets bigger, the capital T gets smaller, and you get tighten it up, right? And that makes sense. A higher frequency signal is going to oscillate a lot faster, okay? A bigger peak here is going to do what? It's going to stretch it out, okay? So what does this do? It does a vertical stretch. What does omega do? It does a horizontal stretch. And you can see that this omega is scaling the x-axis, and then this VP is scaling the y-axis. Okay, good. So we're breaking down the intuition. Let's talk about this theta V next. So theta V is what we call the phase. That is the phase. All right. Now let's see what happens. So again, we have our same equation, V of t equals VP cosine omega t plus theta. And so if we plotted this plot when theta is 0, we saw this as we previously saw in this one. Yep, this is theta equals 0, no problem here. Actually, maybe I should put a V here. I'm just going to put a little V here just so that we're consistent. Okay. And as theta V gets bigger, this guy is actually going to shift to the left. Okay. So if theta V gets bigger, the curve shifts to the left, and we call that phase lead. It's starting to lead, right? And what does it mean to lead? It means it comes earlier in time. Look at the peak of this. Do you see how it comes earlier in time if this is time in seconds, right? Okay, notice the x variable is still, or the x-axis is still time, not theta. Or I shouldn't say still, it is now time and not theta, whereas when we were plotting just that, it's just theta. Okay, now if theta became smaller, and in this case negative, what would happen? It would shift to the right. We call that phase lag. That's how we call it on the streets, phase lag. And lag means it comes later in time. Okay, so Phase lead, phase lag. Bigger theta shifts to the left. Smaller theta shifts to the right. Okay, so what do we have here? Let's review. We have the amplitude or the peak, and that stretches this cosine wave vertically, stretches it, not shifts it, stretches it. What does omega do? Omega stretches it horizontally. And what does theta v do? It slides it or translates it horizontally. So if we wanted to slide it up and down, we just add a constant on the end, right? Okay, not too bad, not too bad. Okay, now maybe another question would be, well, when does that peak occur? So this is the time when the, like on the x-axis, this is the peak, and then we want to find the time when the peak occurs. At this point, you can see that the peak time is negative. If this shifted to the right, you could see that the peak would be positive, if that makes sense, okay? So the peak time occurs when, what? When this guy inside is 0, right? Because that's what it takes for this to be at a peak, right? Cosine of 0 is the peak, okay? So the peak time occurs when the argument to the cosine is 0, right? Cosine of 0 is 1. So how do I make a 0 in here if omega is a constant number and theta v is a constant number? Well, I can just take this argument and set it to 0 and calculate t peak. And that's easy. T peak equal, I'll bring this over, minus theta v divided by omega. Boom, that's it. That's actually the time when the peak occurs, okay? So notice the negative sign, and note if these two are positive, theta v is a positive number and omega is a positive number, which it should always be, the peak is actually a negative number. Does that make sense here? Let's see if that's consistent. If theta v is a positive number, we said it goes to the left. Yes, positive, positive, negative, it does go to the left, becomes negative earlier in time. Okay, I hope that makes sense. Okay, and this is consistent with the plot above for phase lead. Good. Okay, let's, oh, is this the right order? I think that's out of order. Let's look at this plot here, or this these equations here. So we have peak time equals minus theta over omega, and let's look at some other, what do you call it? Let's look at some other equations that are equivalent to this one. We know omega equals 2 pi f, or I don't know, maybe I should put it in tau f, right? Okay, that should be the same. So if I know the frequency, it's the same information as the omega. So this is equal to minus theta over 2 pi f, yep, or 1 tau f. And we know the frequency is 1 over tau, so we can say that t peak is also minus theta over 2 pi times the period, right? Because if I have 1 over t on the bottom, it just comes up. So you can also, this is another way I kind of like to think about it as well, is that the time that the peak occurs is equal to a percentage of the period, right? Look at this, theta over 2 pi. Remember, 2 pi is 1 full cycle. Theta over that is kind of a percentage of the period. And so what does that mean? So let's say I have this theta guy here, right? Sorry, I'm a little loose with that little v on the bottom, but I think you guys are okay. If theta is 0, right, then the peak time, you can see that this goes away, 0. I get no shift left or right. The percentage of the period is 0. Okay, well, what happens if theta was tau or 2 pi? So if I put a tau or 2 pi, you get 6.28 over 6.28, that's 1. So that means it's shifted 100% of a cycle, right? Whether positive, negative, depending on if theta is positive or negative. In this case, if it's a positive number, then it'd be negative. So it'd shift earlier in time by 1 full cycle. You couldn't tell the difference. Well, what if it was pi or half a tau? Then it's going to shift half a cycle, right? The percentage is negative 50% right here. Good. If it was negative pi, it would shift forward by half a cycle. So look at this, positive 1/2 tau. Okay. So this is a phase lead. These are a phase lag, right? Okay, I hope that makes sense. Okay. So if we had a little example, let's say we had this equation, 3 cosine of 5, assuming this is radians per second times t plus 20 degrees, okay? And so the question is, can you please tell me what the amplitude, omega, the period, frequency, phase, and the peak time are, and can you plot it? All right, let's do it. That's easy, amplitude is 3, okay? What is the period and frequency? Well, that's from this guy. Remember, this is omega. So omega equals 2 pi f, So I can just do this divided by 2 pi or 6.28 to get this. And then once I get this, I get the period. Omega equals 5, good. Radians per second, good. 2 pi f or 1 tau f, good. So it's equal to omega over 2 pi or 5 over 2 pi or 5 over 6.28. So 0.796 hertz. Good. Okay. And does that make sense? 0.8. So 5 radians per second, that's not quite a cycle in 1 second. That's like 80% of a cycle. Oh, yes, 80% of a cycle. Can you guys see how these are corresponding numbers, right? These are some checks you want to have. Anytime you get a number, you want to check it in your head. Okay, the period is just 1 over that. Okay, so 1.257 seconds, 1 over f or 1 over this guy. Okay, so the time it takes is a little bit bigger than a second. Okay, that makes sense. Theta is 20 degrees. Now, we want to convert that to radians, so we just have to multiply it by pi over 180 because we know that there's 180 degrees in pi radians, right? Okay, so maybe that's useful, I guess. If you're looking at purely half a revolution, that's where pi could be useful. So this total thing is 0.349 radians. Okay, does that make sense? 34% of a radian. What's 34%? So 1 radian is about 60 degrees, right? This is a third of 1 radian. A third of 60 degrees is at 20. Yes, sir. Yes, good. Okay, what about the peak time? Peak time is minus theta over omega. So remember, when I calculate this peak time, these have to be consistent units. I can't use degrees anymore. I have to use radians, so I have to use this 0.34 guy. I can't use the 20. So 0.34 over omega. So I'm going to plug this, boom, over omega, which was 5. I get negative 0.0698 seconds. Because this was a positive number, we're getting a negative peak time, which is shifting to the left phase lead. Okay, 0.0698 seconds. Okay, not very much, but still shifting to the left. Okay, good. No problem. Okay, let's look at this. Let's look at this plot. So this plot here, here's your cosine. You've shifted to the left, negative 0.0698 seconds. You go up 3 to minus 3, that's the amplitude. You have a period here of 2 pi, what was it, 1.25 seconds or 2 pi over 5 or tau over 5, right? We should put it, I'm just gonna put it here, tau over 5 seconds, okay? And then that's matching this equation. Good, okay, not too bad. So let's look at this next concept called the root mean square. And unbeknownst to you, you might be using this every time when you talk about AC power. Every time you're talking about like 120 volts, 208, 410, that is related to the root mean square. And so what we want to talk about, well, what is the root mean square? These are just the mathematical operations that you know and love. Square root, mean or average, and square, like not square root, but the opposite of that. Okay. And what it is, it's like a time average, and it's very useful for AC current, voltage, and power. We're going to see this RMS a lot. And so this is the definition. Given any signal, it doesn't even have to be AC, it could be any signal. It could be a square wave, it could be a constant, it could be a triangle wave, any time varying signal. This is the definition of the root mean square. So the root mean square is like a function that I can apply to my voltage. So this V of t is any signal. So I look at this formula and you're like, oh, what is this? Oh God, I see an integral and I see dt's. Okay, my eyes are glazing over. No, it's not that bad. Okay, really, when you see root mean square, so let's just go into, ignore this, hide this from you guys for now. It's really square mean root, right? I don't know why they called it root mean square, but it's square mean root because that's the order in which you take the operations. Okay, so let's look at this. So I have my V of t and I square it. Easy. And we can do the mean. Well, mean is the average, right? So what is the average? Well, in a continuous situation, it's this. But what is the average again? You take the sum and you divide by the total number of things, right? Okay. But if you do it with calculus, then you have the integral, which is like a sum, right? So from time 0 to time f, right? So you integrate it. And then you divide by the total number of things. Well, in this case, it would be the time. So 1 divided by tf minus t0. So this fancy integral is actually just the mean, the average. That's how we do it in calculus. And then the square root, boom. So it's not too bad. Square, mean, root, right? Okay. So what we can see is for sine and cosine, if this is v of t and we apply this crazy square mean root operation to it, what we get is that the root mean square of this guy ends up simplifying down to just this. It's really cool. It's the peak divided by square root 2. It's the amplitude divided by root 2. It ignores any of the omega and the t and the cosine thing. It doesn't care. So it doesn't matter if you're oscillating super fast, super slow, shift to the left, shift to the right. The root mean square of any cosine like this, time varying cosine, is just the peak divided by the root 2. That's really nice. Okay. So what does that mean? That means if your peak is 170, your RMS is 120 volts. RMS, and on a test, on a midterm, I want you to denote peak and RMS because they are off by root 2, right? Or square root 2, either 0.7 or 1.4. That's a big difference, 50 volts in this case, right? So that means you're like, hey, Chang-Siu, does that mean that if I say 120 volts, like out of my wall socket, out of my power socket, right? Like this guy right here. So this is 120 volts AC, that it's going all the way to 170 volts and down to negative 170. Yep, that's exactly what I'm saying. It's going from 170 positive to negative 170 negative. Wait, did I say that right? To negative 170. Negative 170 negative is like positive 170. Okay, so yes, makes sense. All right, let's go. Let's keep going. All right, so this is a little proof of it. If you want to ignore the proof, just skip ahead. I love saying that, just skip ahead. And but if you're curious, right, then I'll walk through it, right? And so let's look at this. I can actually take the root mean square. I just rewrote the formula here. And remember, the square, the mean, the root, what does it do? Well, what does the square makes everything positive, right? If I square a negative number, it becomes positive. But the problem is I have units squared, okay? The mean is the average. So if you average the sinusoid, that's kind of useless, right? Because if you average this, what happens? 0, doesn't matter how big it is. But if you average the square, then you will get a non-zero number, right? And it will be dependent on the peak. And then once I do that, you get the units back. Because if you do the square root, you had units squared, then you're going to get units back. So that's the motivation of why they do the square root mean square. Okay, I hope you didn't square. I hope you didn't fast forward. Yeah. Okay. All right. So let's look at this. So you have V of t equals Vp cosine of omega t plus theta. So here's your cosine. If we square it, what do we have? Boop. Good, right? And then what? If you take the mean, what do you get? You get like this, right? So this line is the average of v squared, and then you square root it, you get this. So this is the RMS value, right? Notice the RMS value is less than the peak, right? Yeah, that should make sense because obviously it's 120, 170. Yeah, okay. Now let's look at the proof. Now, if you want to skip ahead, you could skip ahead. Hope you didn't skip ahead earlier. Okay, so let's show ourselves that the RMS of V of t is 1 over root 2 times the peak. So here's V of t, the general form. Recall that 2 pi f equals 2 pi over t. And what we're going to do is we're going to integrate over one period because that's good enough. Okay, so put the definition of here. And now let's look at this. We got to be careful. V of t is Vp cosine omega t plus theta v. Yay. And t0 we'll say is 0 and tf is capital T. Okay, so that means that's 0 and t. Great. So we have 1 over t, 0 to t, capital T, right? And so what do we get here? We get cosine squared, and look at this, square goes here, Vp squared, that's a constant, so it pulls out of the integral, okay? And there's a little nice trig identity. Cosine squared equals 1/2 1 plus cosine of 2x. So you can Google that, look up that trig identity. And notice x, the argument here is omega t plus theta v. Okay, so I take this and I can plug that in here. So I'm replacing cosine squared with this. It's going to be easier to take an integral of this guy, that's why, right, than taking an integral of the cosine squared. Okay, no problem with that. And so what do we see? We have 1. This is very nice and easy to integrate. And over here, this will cancel because the limits are 1 period. Okay, so let's keep going. All right. So if I integrate a constant, I just get t, no problem. And then I got to put my integration limits. If I integrate a cosine, what do I get? I get a sine. right? The derivative of sine is cosine, yep. And I have to have the integration, I have to have that 2 omega, right? That extra 2 omega here. Because if I took the derivative, let's double check. If I took the derivative of this, I'd get cosine of 2 omega t plus theta v times 2 omega. But I have to, if I had that extra 2 omega, I got to cancel it out here. Okay, that makes sense. All right. Okay, that 1/2 also pops out. Yay. All right, so I get a v peak squared, t over 2, 1/2 has gone t, this becomes t, and this becomes the sine 2 omega t plus theta v, okay, over 2 omega. Great. So then what do we get? Okay, oh, good, we even had the check. Great, okay. So if we look at this, now we can pull in our integration intervals, right? So this becomes capital T minus 0, and this becomes, I get evaluated at capital T and evaluated 0. So what do we have here? Look at this, sine of 2 omega t plus theta v minus sine of 2 omega plus theta v times 0. Well, these are the same values, because if you shift a sinusoid, right, by one full period, they're the same value. This whole thing goes away. Gone. That's why I was saying we'll cancel because the limits are one period. Okay, so that goes away, and look at this. I get something very clean. I get t over t, which is gone, and I get a v peak squared over 2 square root. Oh my God. Look at this, v peak over root 2. Beautiful. The root mean squared, this crazy operation on that cosine, turns into something very clean. Just v peak over root 2. I tell you folks, I give you my best. I give you my best. Okay, so now let's go to this example. So let's look at this. 169.7 cosine of 377t plus 30 degrees. All right. The question asks, what is the amplitude? Oh, it's easy. What is the RMS? Oh, that's again easy. What is the period? Easy. Is the peak to the left or right, or t equals 0 when, and when is the peak time? Easy. And then plot. Okay, we got this now. Now that we have this nice review, we got this. Okay, so this, by the way, would be an example of a AC cosine, a sinusoidal wave that is coming out of your wall. These are some numbers that could potentially be there, right? Okay, what is the amplitude? 169.7. What is the RMS? It's the amplitude over root 2. 120. Oh my goodness. Yes, 120. Actually, we already talked about that. Not that surprising. Okay, what is the period? Period is 1 over f. F times 2 pi equals omega, or f equals omega over 2 pi. So I can take this 377, which is in radians per second, and divide it by 6.28. So this is equal to omega over 6.28. Okay, what do I get? 60 hertz. Nice. So that's a good fact to remember. So 60 hertz corresponds to 377 radians per second. Good. Okay, what's the period? Period equals 2 pi over omega, which is 2 pi or 6.28 over 377, 0.017. So 1716 milliseconds is one period. What's 17? Like, what's a thousandth of a second? That's like one, so 1 second is 1/1000. So if I chop that into 1,000 times, that's a millisecond. My brain cannot fathom how fast that is, but that's really, really fast. So that's a kilohertz, all right? So if you go 1,000 of a second, that's corresponding to kilohertz, right? I cannot do that. And then, but this is a little slower. It's 1716 of those, right? That's how long it takes to go from 170 volts to negative 170 volts back up to a positive 170 volts. That's pretty ridiculously fast by human standards, but actually ridiculously slow by computer standards. Pretty crazy. Okay. And since the phase is positive, does it shift left or right? It's going to shift to the left. It's going to phase lead. It's going to come earlier in time than if this was 0. Okay. And then what is the peak time? Well, we can use our nice formulas, minus theta over omega. So minus 30, I got to convert it to radians. So pi over 180. Notice the degrees cancel and I'm left in radians. So I get radians divided by radians per second, right? So that's going to be left with seconds. Good. And I get negative 0.001389 seconds. Good. Okay, so it's going to shift just a little bit to the left, right? So it's going to shift a 16th of a percent of the period to the left, right? Because if one period is 17 milliseconds, this is 1 millisecond, it's 1 over 17th of a percentage to the left. Okay, now we can plot. So Not perfectly to scale, but let's look at what's going on. This is T peak, it's shifted to the left, good. We have the period of 0.017 seconds, and it's going all the way up from 170 volts down to negative 170 volts, okay? So that's what it looks like. That's what this plot looks like. And now that we've done this nice review, you could, if I gave you any of this information, you can make this plot. And if you had this plot with this information, you could get that the equation, no problem. Okay, so let's go over to Excel and do this exact same example with these numbers and see if it actually plots out this same curve. 0.017 seconds, right? Remember that period. Remember this 0.0013 kind of shift earlier in time from the 0. And remember this 170 to negative 170, okay? All right, let's go to Excel. So go to Excel, let's see, share screen. Okay, here we are in Excel. And so I have everything blank. I have my cheat sheet on the back just in case I mess up, but here we go. So omega, what is omega? So let's say 377. Okay, and so what I'm going to do is F, what is that? F, just so we know it, it's this number divided by 2 divided by pi. And so if you put those two parentheses, it actually gives, look at that, 60, pretty close, 60.00 hertz. Okay. And what was theta? Theta in the problem said 30 degrees. And how do we do theta in radians? Well, this is this number, okay, times pi, I gotta do this, pi divided by 180, okay? Does that make sense? 30 degrees, remember how much, that's like, so what's 1 radian? 1 radian is like 60 degrees. Okay, so that means 30 degrees is gonna be like half a radian. Excellent. Okay. What is the RMS? So the RMS, well, we know that the RMS is 120, and we know that the peak was 169.7. So this is equal to the peak divided by the square root of 2. Look at that, 120 volts. Nice. Okay. So let's plot some time here. So we can pick, I don't know, negative, let's go from negative let's see. So it was 17, let's say it was 17 milliseconds for one period. So let's go negative 0.02. How about that? And then we're going to fill this out. So we'll go negative 0.0199. Yeah, it should be good. And then we go negative 0.0198. Okay, so I'll put those three numbers, and then that way Excel can pick up the pattern, right? Does that make sense? Yep. And then let's just drag this over. We'll make a lot of them. Oh my God, it's gonna be a lot. Keep going. Okay, that's good enough. Wow, that's a lot. All right. And then, so we went from negative to positive. Okay, so now, okay, this is V. This is gonna be equal to what? The peak, right? The amplitude times cosine of omega, which is this one, times time, which is this one, because time is what's going to vary, plus the phase in radians, because I need to make sure they're all the same units. And I believe Excel takes radians, so I got to have the radian, all these in radians. Okay, so you guys can see. So peak, good. Omega in radians, good. Radians per second. A9 in time, good, seconds, and then B4 in radians again, good. Now here's what I also have to do. I don't want these to propagate, so I got to put dollar signs there. I don't want this one to propagate. I do want time to propagate, but I don't want the phase to propagate. I want those just to stay constant. I want the A9, the time, to propagate, okay? So, okay, so that's great. So now I can take this and, oh, nice. Good. So I have that. Great. Okay. And it's good. I'm seeing varying numbers. Good. And then I can even square it, right? Because I want to do the whole root mean square, because this is going to be the root mean square. So watch this. I'm going to take this equals to this times itself. Good. And then I can propagate that. Okay. So remember, root mean square is actually square mean root. Okay. Let's keep going. All right. The average, okay, so this is equal to the average of this entire column, right? So take the average of this entire column. All right, and yay. Okay, that's the average. And now I'm going to take the equals to the square root of this number. Oh, nice. Nice. 120 volts. Yes. I mean, plus or minus, right? Yeah. So if the peak is 170, the root mean square is 120. Look how close these numbers are coming. This is just straight up using 1 over square root of 2, but this is actually performing the operation. It's squaring it, taking the average, and then doing the square root. Look at those numbers come together. And I bet you if I had more time, this would get converged closer and closer to 120. Okay, now we should be able to plot it. So let's do this. So I can go insert, and let's insert a, what is it, scatter plot. Insert chart, insert, okay. And I can go in here and what do I got to do? I got to select the data. What do I do? Select data, okay. And I'm going to add, and X values, we're going to add the time. All right, so let's go. Keep going, okay, there we go. Okay. And then we're going to add the Y values, and let's see, let's go back up here. Oop. Okay. Let's go all the way down. All right. Done. Okay. Okay. Let's see what we get. Let's see what we get. Nice. Nice. Look at that. That is V of t. And let's double check. So can I spread this out a little bit so that I see what's going on? All right. So remember, our period was 16 milliseconds. Look at this. From here to here, look, we got a 15. Yeah, but we got a little extra here. And then our peak time, what was our peak time? 0.00313 negative. Yeah. If this is 5 thousandths, yeah, this is about 0.13. Yep, very good. And what's our voltage going? 170 to negative 170. Fantastic. This is our V of t. So the x-axis is time and the y-axis is voltage. This is what a really nice signal coming out of your wall would look like. And if you wanted to even plot, we could even add one more chart just to plot the V squared. It should just look like this, but like, you know, no negatives. So we can just do that real quick. Insert chart. Actually, could I do it right on here? Can I add a new line? Maybe it's a little, let's see here. Add, no, I'm not, I'm just gonna make a new one. Insert chart, okay, another one. And we wanna add select data. And so we'll add another series. X values is gonna be time again. All the way down, good. And the Y values are gonna, actually, can I just do this one? So go back up. That's what I should have done in the first place. Oh well. Come on, a little faster. Yep, so this is the V squared. And then okay, okay. Nice. So if I plot this on the same scale as the other one, look at this. Notice how it's all positive, right? So this is matching this one, and then this is just flipped over, okay? And so if I could take the average of this, and I could take the square root, and I would get the RMS, right? And you can see, can you see that the average of this is about 1,500? Yep, perfect, 1,500, and then the square root ends up being 120. Excellent, excellent. Okay, well, I hope this helped you get introduced or reintroduced and reviewed to your AC stuff, your Trig stuff. So all that stuff that was rusty, I hope it's useful. And yeah, I'll see you in class and enjoy. Have a great day. Bye.